out from the root set in one pass. So one pass, only the live objects, and when you're done, you have total defragmentation. So here's how it's going to, oh, by the way, some other things with it. The copy frequency is proportional to the size of the semispace. So if I have small semispaces, it'll copy very frequently. If I have large semispaces, then basically it will copy much less frequently because it's less frequent that each of those then fills up. So let's look at the algorithm that we're going to use for doing stop and copy. It's called Cheney's algorithm, and the key thing to understand is it is a breadth first traversal out from the root set. It is not depth first. So mark and sweep, most implementations will go depth first. In other words, you visit the first thing out, so you go out from that, so you'll have a root set, you'll visit the first thing, and then if you're doing depth first, like mark and sweep, you then recursively visit its children, and then you basically recurse all, or pop back out of the recursion to go down a different branch of the tree. Cheney's algorithm is by its nature breadth first, not depth first. And by doing it that way, we actually guarantee that basically that sort of parents are copied before children. Okay. Now you might think, well, depth first does that if it's actually a tree, but if you have a DAG or even something with cycles, then there's no guarantees of that with depth first. But with breadth first, you're guaranteed, you're always visiting parents before children. So here's how we're going to do it. So suppose that this is the structure of objects in the heap. We'll have two things in the root set. One is object A, one is object B. I apologize, these are a little small. Hopefully the labels are big enough to be readable. So A and B, objects A and B are part of the root set. A has some pointers to other things, B has some pointers to other things, and those have pointers as well. So it's going to be breadth first. The first thing that we're going to do is when we start, the two space is totally empty. Remember I said we're going to keep one pointer that's the base of the free memory? Well, we'll use that during the copy phase, not only during the actual allocation kind of phase. So when we start off, the free pointer is just right at the base of the two space. And the first thing we're going to do is we're just going to copy over everything in the root set to the address of the free pointer. So we copy A to the base of the free space, the two space, and we update the pointer. And then we copy B over and we update the pointer. So once we've copied over both roots, A and B have been copied over, and the free pointer is pointing after them. Everybody okay with that step? So you just copy over all the objects in the root set, and now you keep incrementing the free pointer as you copy them over. So now we've copied over A and B, we're going to introduce a second pointer. And this is the key thing with Cheney's algorithm. This is called the scan pointer. We're going to start scanning what we just copied over. Okay. So initially, the free pointer and the scan pointer start at the same place in the beginning. We copy over the root set, and the free pointer gets incremented. So you'll notice there's a lag here between the scan and the free. The way we know we've copied everything is when that scan pointer catches up to the free pointer. So we'll start off with the scan pointer here. And then we'll say, oh, the scan pointer points to object A, the copied over object A. And so what we're going to do is we're going to then say, oh, well, let's look at A. Does it have any child ones? Now, again, these things could be objects or to other data structures or whatever that have data, but these might have pointers to other objects. So we're only going to look at the pointer structure. So A points to object C, so we're going to copy it over. And A also points to object D, so we copy it over. So we're going to look at the first thing. So the scan pointer is right here in A. We're going to look at the first thing in A and say, Is this a pointer to some other object? If so, we're going to do two things. We're going to copy it over and update the free pointer. We copy it to the current free pointer and update the free pointer. And then we just increment the scan pointer saying, all right, we've already scanned and copied that. Everybody okay on that step? Because everything else is just repetition from there. So we scan A, we see A has a child C, so we copy it over and we increment the scan pointer. And then same thing, A points to D, so we copy it over, increment the scan pointer, and the free pointer is updated. Yeah?
You answered it.
Okay, sorry. I saw your hand go up, I just wanted to
No,
finish the-
yeah,
the
because
thing
I was
with
just
A.
confused why I only went halfway through A.
Yeah, so we're going to start scanning A.
Got it.
Now remember, we know the type of the remember there's headers and stuff getting copied over. And so when this is done in Java, those headers actually indicate type information. So I know what type object A is, so I can look at the header here. I know what type object A is, and I know what offsets within that object are pointers to other things. And so I copy, so now A is completely scanned, and I've copied over C and I've copied over D. Then I keep scanning. Now I'm reaching B. So notice I don't immediately start copying over the children of C and D. It's breadth first. I'm going to keep scanning what's already been copied. So now I get to object B that was copied over. Well, B has a child E. So I copy E over at the current free pointer. So you're always copying to the current free pointer and incrementing the free pointer by the size of whatever you copied. And then then we just increment the scan pointer. So as we keep progressing through, we scan this first thing in B. We then scan all the rest of B, which forces F to be copied over as well, and so on, and so on, and so on. Like I said, eventually this scan pointer will catch up with the free pointer because you've copied over all children that there are, and you've scanned them looking for any other children. And at that point, when the scan pointer catches up to the free pointer, you know you have copied over everything that's live. And notice it never even visits the things that are dead. Okay? Yeah?
So how do you handle cycles then?
Good. All right, so we'll talk about this forwarding pointer and then the bell's about to ring. So what if we actually had, so even without cycles, what about just a DAG? What if it turned out that B pointed to D instead of to E? Okay. Well, I don't want to copy D over again while I'm scanning B. So here's the key thing. And we'll wrap up with this. At the address where C used to live here, actually let's start with A. When I copy over A, I'm going to modify the header of this ghost copy of A and leave a forwarding address. So I'm going to I'll mark the header that says, this has already been copied, and here's the forwarding address in this space of where it's been copied to. And so when I'm scanning B and I find a pointer to D, I look there and I say, already copied. Okay. Oh, sorry, one other key thing with this. As I copy it, you'll notice I'm actually updating the pointers to point, as I scan through pointers here, I'm updating them as I copy the data over. Here, I would just simply say, already copied over. Let's modify that field in B, that pointer, to now just point to where I already know I copied it to, using the from header, or the forwarding address.